Hello again, welcome back. Today we are talking about a new gas law that's called Boyle's Law. Oh no, not Boyle's Law, we already done Boyle's Law. So we checked, done that. Okay, so now today we're talking about Charles' Law. Okay, so what we talked about in the last video, or if I didn't make the last video, but the one I posted on Canvas, is Boyle's Law is P1 V1 equals P2 V2. It's only about these two variables, pressure and volume. Pressure before, pressure after. Volume before, volume after. Okay, at Boyle's Law, what is constant? What doesn't show up in here means it stays the same, which is it's a constant. And so the constant we have here is temperature. Temperature stays constant, and also the number of gas molecules. Okay, but the main thing is that temperature stays constant. It does not change. For Charles' Law today, we'll talk about the equations V1 over T1 equals V2 over T2. What variable is missing in here? Pressure. There's no pressure, so pressure is constant. So if you have a pressure, you can pick any pressure, and it's before and after is the same. So then it cancels out anyways. That's why it's not in the equation. Okay? Anything that's constant means it stays the same. Okay? Constant stays the same. So it's basically crossed out. It's not in the equation. It doesn't show up in the equation. Okay? Because it stays the same. So in other words, Boyle's Law again, temperature is constant, you don't see temperature. Charles' Law, pressure is constant, you don't see pressure. So for Boyle's Law, V1 over T1 equals V2 over T2. This is a ratio, okay? Anytime you solve a ratio, you got to multiply. You cross multiply and divide. It's just basic algebra. Just like if you had 2 over 3 equals x over 9, for example. All right? In math, what would you do? You'd multiply 3 times x, so it's 3x. 2 times 9, which is 18. You cross multiply, and now you divide. Divide by whatever's with the x, then you get x is equal to 6. Same thing here. It's just different numbers. Now we throw in volume and temperature. You have to recognize those things. And the key thing in this formula is that temperature must be in unit, must be Kelvin. Must be Kelvin temperature. Okay? And how do I get temperature if Kelvin if I have degrees Celsius? You add a number to it, and that magical number is 273. So if it's 10 degrees Celsius, I'd add to that, it'll be 283 Kelvin. If it's negative 20 degrees Celsius, I'll add to that, 273. Then I would get 253 Kelvin, right? If you don't know how to do negative numbers, use a calculator. You're not expected to do those computations in your head or on paper. Just use a calculator and be able to do that. Okay? So you should have this paper in front of you, Charles' Law. Let's go through a couple of these so that you know what you're doing, or you kind of have an idea of what to do. So look at number 1. It says calculate the decrease in temperature. We'll change that. Change that to the final temperature. Final temperature. Calculate final temperature when 2 liters of gas at 20 degrees Celsius is compressed to 1 liter. So list it out. V1 equals T1 equals V2 equals T2 equals. Okay? V1, 2 liters. T1, 20 degrees Celsius. V2, 1 liter. T2 is our X. We're looking for that. Okay? We're looking for T2. So, what do we need to do first? We check, again, remember, temperature must be in Kelvin. So is temperature in Kelvin? No. So we have to change that to Kelvin by adding 273. So we add 273 to that. You get 293 Kelvin. Okay? Now we can plug into our equation. V1, which is 2, over T1, which is 293, equals V2, which is 1 over X. Okay? Now we cross multiply 2 times X equals 1 times 293. So we write that down. 2x is 2x equals 293 times 1 is 293. Divide both sides by 2. Divide both sides by 2. Then when I do that, this here cancels out. 293 divided by 2, that's 146.5 Kelvin. Okay? So let's just say, what if the question asks you to change it back to Celsius? Because logically, it makes sense to change it back to Celsius because our first temperature is Celsius. So we need to change this Kelvin back to Celsius. What shall we do? Okay. To get to Kelvin, we added 273. So to go back to Celsius, we would subtract 273, and that'll give us a negative Celsius answer. Okay, so make sure you know how to do that. To get to Kelvin, you add 273 to the Celsius. Right here. Celsius, add 273. To get to Celsius, it's whatever Kelvin is minus 273. That'll give you back to Celsius. Okay, keep that in mind. You'll have to do that sometimes. Most likely on the next quiz. Okay, when I make my quizzes, I will always ask you to, well, not always, but most of the time I will ask you to change it back to Celsius. All right, let's do one more so that you kind of get the hang of this. Let's do number 7. At 27 degrees Celsius, the gas has a volume of 6 liters. So, from my experience, I'll write smaller. I'll write them closer to each other so I have more room to work. V1, T1. V1 is 6 liters. T1 is 27 degrees Celsius. V2 is X. We're looking for V2. T2 is 150 degrees Celsius. So notice they're both in Celsius. Okay, what needs to happen? We need to change them both to Kelvin. We need to add 273 to both of them. Plus 273, that's nicely 100. 300 Kelvin. Add 273 here. 423 Kelvin. Alright, so now I plug into my equation. V1, which is on top, 6, over T1, which is, oh, this is 1. I don't know why I put 2 there. T1, which is 300, equals V2, which is X over T2, which is 423. Okay. So now I cross multiply here. Cross multiply there if you want to. Just because that's how we do that. 6 times 423 equals 300x. Divide both sides by 300 now. And you get your x, which is your volume in liters. It'll give you the same unit as what you start with. So the volume, the unit for volume has to match. The unit for the volume could be centimeters cubed, milliliter, doesn't matter. The volume unit does not matter as long as they match. Temperature just must be in Kelvin when you use this equation. Okay, and so take that divided by that, and you get your answer. Okay. Well. It's a short, sweet video here. Again, just list out all your variables here. Sometimes standard temperature, like number 6 here. It tells you a gas occupies 1 liter at standard temperature. Remember, standard temperature is STP. Standard temperature is 273 Kelvin, just the standard, just the number. And standard pressure, we remember from the Boyle's law unit, is 1 atmosphere. It is also equal to a bunch of other stuff like 760 millimeter of Hg, 760 torr, 101.3 kPa, or 14.7 psi. So make sure if it says standard temperature, that is a number. Okay, that represents a number. So here, like number 6, V1, which is 1 liter. T1 is the standard temperature, which is 0 degrees Celsius or 273 Kelvin. What is the volume at the new temperature? So we're looking for V2 here. And then the new temperature is 333 Celsius. You still need to change that to Kelvin by adding 273. It's going to be a big number, but that happens, guys. This is all hypothetical situations, so these numbers could look really weird, okay? So that's 606 there. So you plug all those in to your equation and solve for that V2. It's fairly simple. But you have to recognize which numbers which unit belongs to pressure, which unit belongs to volume, which unit belongs to temperature, and then change temperature to Kelvin. That's the most challenging thing for this part. Okay, good luck. That's the end of Charles' law here. We'll continue with combined gas law in the next video. Bye bye.